Me. All right, last time we were talking about molecular orbital theory and how it can explain bonding in organic molecules, and we started with our simplest of all organic molecules, hydrogen. And we talked about how MO theory allows you to take atomic orbital wave functions, and combine them together to get wave functions that are delocalized over the whole molecule. And the math requires you to consider both the plus and minus combinations of, say, two atomic orbitals that you're bringing together. By analogy to standing waves that can have positive or negative amplitude and can interfere with each other, we call the plus combination constructive interference and the minus combination destructive interference. And as we talked last time, we discussed how you can get a bonding orbital by combining the 1s orbital from one hydrogen with the 1s orbital from another hydrogen, and that orbital is lower in energy than the original 1s orbitals were. And there were two reasons for that. One is that electrons that would be in that orbital tend to spend a lot of their time between the two nuclei, where they experience two nuclei instead of one. So just from a potential energy point of view, Coulomb's law and whatnot, that's lower in energy. But then we also talked about how that new orbital that we made, the 1s plus 1s orbital, is more spread out and its slope changes more slowly, and therefore the kinetic energy of electrons in that orbital is lower. It's kind of fascinating. One of the reasons that electrons are involved in bonding is because they can slow down a little bit. And that energy difference is reflected in this energy diagram where the new molecular orbital is lower in energy than the orbitals were where we started. Now that difference in energy is related to the strength of the bond. For a carbon-hydrogen bond, or for a hydrogen-hydrogen bond, it's about 100 kilocalories per mole. And that is a per electron number. This energy difference here is a per electron number. That is, suppose this were, 4 arbitrary stability units. You put one electron down here, you gain 4 stability units. You put a second, you gain another 4. So overall, you're 8 stability units more stable than you were when you started. And this is why bonds form, because it allows electrons to move lower in energy. Now, so far, that picture is actually identical to what valence bond theory would tell you, that you get the bond between the two hydrogens by overlap of the two atomic orbitals. One other term I'm not sure I've introduced is we're going to call this bonding orbital a sigma bonding orbital because you form it from end-on-end overlap. That is, the two individual atomic orbitals actually touch and overlap with each other. Okay? It's not as apparent with these spherical orbitals, but if either of those were p orbitals as an example, or sp3 type orbitals, and they approached each other with the large lobes interacting end on end, that's sigma overlap. And one of the interesting features of sigma overlap is you can take one partner and twist, and it doesn't change the orbital overlap, and the bond stays the same. So the new thing for MO theory was that we have to also consider this minus combination of the two original atomic orbitals. We call that destructive interference. Because you're subtracting one from the other, there is a difference in the mathematical sign of the wave function on one side versus the other side. And if we're positive over here and negative over here, you've got to go through 0 to get there. The wave function is a continuous function. So just like our slinky standing wave can have positive or negative amplitude or can go through 0, so a wave function can be positive, negative, or go through 0. And this dotted line here indicates a node where the wave function is 0. And importantly, the wave function squared, which gives you the probability of finding an electron at that location, is also 0. So that means if you were to put electrons in this orbital, you could observe the electrons on either side, but never along that node. Because there's no electron density in that orbital in between the two nuclei, we call that an antibonding orbital. And we talked last time about how if you were to take one of these electrons and promote it up to the antibonding orbital, you would break the bond. The one reason for that is this antibonding orbital is more destabilized relative to your starting point than the bonding orbital is stabilized. So this energy difference here is larger than this energy difference here. So if you promote an electron all the way up, it cancels out the effect of having the electron in the bonding orbital and the bond breaks. Okay. Any questions you want to ask about that? Yeah.
I can't get into the Zoom, so
Oh, you can't get into
I'm
the
not
Zoom?
really helping out here, so
Okay, that's fine. I wonder if it takes some time to, yeah, to add you to the system. Okay, sorry about that, technical difficulties, but we're good to go. Yeah.
If there are 2 electrons in the bonding orbital and 1 in the antibonding orbital, is it still destabilized to the point where it's normally favorable?
It's a good question. If there's 2 in the bonding orbital and 1 in the antibonding orbital, like if I just dumped an extra electron into hydrogen, would it still be stable? It would be about half a bond stable. Yeah. We wouldn't really know how long it would last. Would probably depend on what the environment is and whatnot. Maybe you could find it out in space somewhere. I don't know. Yeah. What else? Yeah.
The arrow with the energy gap, one is denoted delta EAB and one is delta EB. What, like why are they?
AB is for antibonding.
Oh, sorry. Okay. Yeah.
Yep, and B is for bonding. Sorry about that.
Yeah, I thought I was talking about the orbitals.
Okay, cool. Good. What else? Yeah.
So for the antibond, since the electron density at that node is 0, there's no negative charge between the two positive poles repel each other? Is that how that?
Well, so because there's no, I mean, I guess if that were all there was, then yeah, I suppose the positive charges of the nuclei would repel each other. Basically, when you bring a molecule together, you got to pay for having the 2 positive charges close to each other. You do that by having the 2 electrons sort of in between. But if you were to put electrons in this orbital, they would tend to be actually pulling away from the space between the 2 nuclei, and they would cancel out any benefit to bonding at all, and then you've got to deal with that repulsion again. Yeah. Okay, cool. What else? Yeah.
What's the HA and the HB?
H is hydrogen.
Oh,
I should have chosen different letters. I realize there's lots of A's and B's all over there. I apologize. It's hydrogen A and hydrogen B. Yeah.
What does the del stand for again?
The delta there means difference in energy.
Upside down.
Oh, the other one is, the upside down one is the second derivative of something with respect to space. Yeah. Okay. Anything else? All right. So, so far, the valence bond picture of hydrogen, where you have 2 electrons shared between the 2 atoms, and they come from overlap of 2 atomic orbitals. That's actually pretty much the same thing as we get from MO theory, only MO theory tells us there's actually an empty orbital up there, an antibonding orbital, that we need to be worried about, need to be thinking about. However, the differences between MO theory and valence bond theory become clearer once we start looking at more complicated molecules. So I'm going to draw the Lewis structure of methane. And in doing so, let me just remind you that in Lewis structures, solid lines represent pairs of electrons shared in a bond between 2 atoms. The wedge represents a bond coming out at you, and the dash represents a bond going back into the page. When you look at that, you need to be thinking, oh, that is a tetrahedral carbon. It's sp3 hybridized. The bond angles are 109.5 or so. And let's see. And this is an image of what that tetrahedral structure looks like. And if we line it up like that, you can sort of see what we're trying to communicate. Okay? Now, the valence bond theory picture of methane would have told us that that bond comes from overlap of an sp3 orbital on carbon with a 1s orbital on hydrogen. Of course, an sp3 orbital looks like this, a large lobe on one side and a smaller lobe on the other side. Node at the carbon nucleus, a 1s orbital is simply, there are no nodes in the 1s orbital, and we would conceptually make the bond by making those two overlap with each other. And the orbital we would draw that would come from overlapping those two would start at the carbon and would extend and envelop the hydrogen and hold the two atoms together. But there's another way, and that's the valence bond theory picture. And valence bond theory would predict that methane has 4 identical carbon-hydrogen bonds, sigma bonds, and they're all at the same energy. In contrast with MO theory, we can start to make orbitals that are combined and span more than 2 atoms. Okay? So in our MO theory treatment of methane, we're going to take the available atomic orbitals in our molecule, and let's just think about what they are. We start out, methane is CH4, we start out with 4 1s atomic orbitals, and then on the carbon we have a 2s orbital, and then we've got 3 of the 2p orbitals, y, x, and z, pointed in orthogonal directions. Overall, that's 8 atomic orbitals. And we're going to combine them together by constructive and destructive interference, or by adding and subtracting to get new molecular orbitals. Now, what I show you here is not something I would expect you to be able to derive on your own, but it's informative because it's your first example of an MO that's delocalized over more than 2 atoms. So the math of MO theory tells us that we're going to mix them together, and there's a conservation of orbitals principle that happens. It's if you start out with 8 atomic orbitals and you mix them together, you must get out 8 new molecular orbitals. So we're going to generate 8 molecular orbitals. I'm only going to show you 4 of them. We're going to ignore the higher energy empty ones for now. All right, so our first combination could come by mixing the 2s orbital from carbon with each of the 1s orbitals on hydrogen, all constructively, all with the same wave function sign. I'm going to draw the Lewis structure of methane again to show you in a picture what I mean by adding those orbitals together. Together, those orbitals are going to make molecular orbital 1, which is only going to be one of our 8 molecular orbitals. But if I were to combine the 1s orbitals on the hydrogens with a 2s orbital on carbon, all with the same wave function sign, those are all the wave functions I'm adding together to get the new one. It would look like this. I'm going to draw the positions of the atoms in the same location as they were in my Lewis structure. But I'm leaving out the lines now because I'm thinking about this as a single molecular orbital that spans all of these atoms. And that molecular orbital can only accommodate 2 electrons. Okay? So in this molecular orbital, those 2 electrons would be delocalized across all 4 hydrogens and the carbon in the middle. And at this point, we lose our focus on sigma bonds entirely. You might say, which one of the 4 bonds of methane does that pair of electrons account for? And the answer is, if you were to ask an MO theory person, they would sort of look at you, tilt their head, squint a little bit and say, what is this bond that you were talking about? I have no idea what you're talking about. The electrons aren't in a bond, they're in a molecular orbital that spans the whole molecule. So it's kind of a weirder picture of things. My drawing may not do it justice, so I'm going to open up a program called Spartan that allows us to see what some of these MOs look like. Here is the methane molecule. This is the lowest energy, or this is the orbital that we just drew, the one where a pair of electrons is delocalized across the whole molecule and the wave function sign doesn't ever change. All right. Yes?
So in reality, there are 8 of those.
Yes. Yeah, there'll be 8 different molecular orbitals. 4 of them will be filled, and 4 of them will be empty. One potential item of confusion, sometimes when I'm trying to show the particular combination of pluses and minuses that gives us this new molecular orbital, some people look at this and say, hey, you've already added 5 MOs together. You've already taken care of 5 of your 8 choices. The answer is no. 8 atomic orbitals, 8 unique MO combinations of those atomic orbitals. So this is just one of them, and it has the 2 electrons spanned over the whole molecule. I'm going to show you one of the other 2, and then I'm going to show you, let's see, there should be 8 molecular orbitals. We'll only worry about the bonding ones, not the antibonding ones for now. And I will show you only one of the other 3 MOs that are bonding in methane because the 3 other ones that we haven't done yet all sort of look the same. They're only oriented in different directions. Kind of like the 2px and the 2py and the 2pz look the same. They're just oriented in different directions. All right. So what we'll show you next is how you can account for bonding. This will show you how MO theory deals with bonding in methane without having to do orbital hybridization at all. So I'm going to copy our image of methane, and I'm going to erase the 2p orbital in the middle, and I'm going to switch the sign of the wave function on 2 of the hydrogens. Okay, so if we were to start to write out what this orbital might be, we're going to have a 1s orbital plus a 1s orbital minus another one minus another one. Okay. Well, what have I got left of my atomic orbitals? I haven't done anything with the p orbitals yet, and it just so happens that the p orbitals are uniquely suited to be able to deal with this situation because a p orbital can overlap with those 2 1s orbitals at with the same wave function sign at the same time as it can point in the other direction and overlap with the other hydrogens with the other wave function sign. Now, the way we've drawn this p orbital that we just drew is in the plane of the page. The yellow or the orange lobe bisects the space between these 2 hydrogens, the ones that are in the plane of the page. The purple lobe in our atomic p orbital is also in the plane of the page, and it bisects those 2 hydrogens on the other side, one of which is coming out of the page and the other going back into the page. so that if we were to draw what this orbital really looks like, we would have one large sort of hot dog shaped lobe on this side, and then with opposite wave function sign, another large lobe on the other side, oriented at a slightly different direction. And of course, we could do that as well without showing any of the original bonds from our Lewis structure, just preserve the locations of the atoms. Here is the orange lobe, and that orange lobe would tend to pull the hydrogens and the carbon together, as would the purple lobe. And once I'm done shading in the color, we'll switch over to Spartan and I'll show you what that looks like. So instead of orange, we've got a red lobe on our left and a blue lobe on our right. And notice how those two lobes are sort of oriented crossways relative to each other. Okay. So that's one of our options. There are two others that are like that, and they just happen to use the two other p orbitals that we still have to deal with. There are higher energy orbitals, but they look strange, and we're really not going to worry about them because I don't know how. That looks like an interesting children's toy. Huh. 3D print that and give it to your nephew. All right. If you look at these two orbitals, which one do you think is lower in energy? Go ahead.
I think it's the one at the bottom. I don't know if it has anything to do with like division. There's like a node.
Okay, you're right. There is a node. There is a node that goes right between those two lobes. We can see it in Spartan. Instead of being a plane, it's more like a surface, but that's a place where electron density goes to 0. All right, the one on top doesn't have any nodes. So you remember the slinky analogy. The more energy we put into the slinky, the more the frequency was, the more nodes we had. So of these two orbitals, one with 0 nodes and one with just 1, which is higher? Yeah, the one with 1 node. One node is always, the one with 1 node is going to be higher than the one with 0 nodes. And so, as I said, if we were to draw an energy diagram for methane based on MO theory, we would have 1 lower energy orbital, MO1, and then 3 higher energy orbitals. And then maybe this is our break-even point where the non-bonding atomic orbitals tend to be. And then up here, there would be 3 antibonding orbitals. There would be 4 antibonding orbitals, 3 the same energy and 1 different. We have 8 valence electrons, so the 4 bonding orbitals are filled and the antibonding orbitals are not filled. So that's the difference in MO theory between between MO theory and valence bond theory for methane. MO theory tells you you've got 1 of those pairs of electrons that's lower in energy, but all of them are delocalized over the whole structure. Valence bond theory would tell you, oh, actually, no, I have 4 identical sigma bonds. And you can actually measure this energy difference experimentally. You can tell that there are 2 different kinds of electrons in methane. And so, at least for that experiment, the MO theory is a more complete picture. However, that distance is not really that much. And it turns out that it will be easy for us, instead of being MO theory extremists or valence bond theory fundamentalists, we might try a more hybrid approach. And in that hybrid approach, we're going to think of sigma bonds as localized between 2 atoms. So we're not going to for the most part, with sigma bonds, we're not going to do what we just did in methane, where we think of pairs of electrons delocalized over the whole atom. But unlike valence bond theory, we're going to remember the antibonding orbitals because they will be important when we need to describe the kinds of reactions that molecules do. All right. So for our purposes, it'll be fine for us, like we were saying above. It will be fine for us to draw a pretend energy diagram for methane where we say you have, here's your break-even point, you have 4 identical sigma bonding orbitals, and you have 4 identical sigma star antibonding orbitals, and they're all, the bonding ones are filled with electrons. Even though we know that doesn't reflect a measurement you can make, that's going to be okay for us for the most part, right? So why did I even bother showing you this stuff about methane? Well, I didn't used to, but I geek out about it because I think it's cool. So sorry, to see something I think is cool. I do want you to know the difference, though, between MO theory and valence bond theory, which is valence bond theory focuses on the bonds. MO theory focuses on delocalized electrons over the whole molecule. Now, there will be a part, there will be an area of molecular structure where we're gonna have to go back to MO theory. And that has to do with resonance. But before we get there, I want to just pause and see what the questions are and give you guys a chance to respond. I guess Emma, the TA Emma, is monitoring the chat online. Emma, if there's something I need to say, go ahead and unmute yourself and speak up, and I can address the question. Questions you guys have? Yeah.
Just to make sure this last diagram you drew there, it's the hybrid in the sense that it's almost like the SP3 where we're doing the 4 that are at the same energy level.
Exactly.
Just taking into account there's antibonding and bonding.
That's right. Yeah, the question is about this energy diagram, and does it come from just thinking about sp3 orbitals on carbon interacting with 1s orbitals on hydrogen? Yes, it's exactly that way, only we're remembering that there's antibonding orbitals. And this picture gets us close enough to the truth to get the right answer in most cases. Okay? Anything else I'm missing for you folks at home?
Can I ask a question?
Sure.
So that energy diagram that you wrote with the antibonding and bonding, that's methane, and then the one you did a little ways up in your notes is also methane. The difference is that this one is just molecular orbital theory, and then the bottom one is the hybrid.
Exactly. Yep. So the question is, the difference between the two energy diagrams I did is this one is from MO theory exclusively, and then this is our hybrid approach. Doesn't capture all the features of experiments, but it's useful enough and simple enough, actually, that it's that's what we'll sort of stick with.
Can you explain the molecular orbital theory energy diagram one more time?
Yeah. So in methane, we saw that our lowest energy orbital was this one that delocalized across the whole molecule and had 0 nodes. And then we saw that there was a degenerate triad of a degenerate group of 3 orbitals that were equal in energy, that all looked kind of like this, with a lobe of one wave function sign here and a lobe of opposite sign on the other side. And we said that those with 1 node must be higher in energy than the ones with 0, than the one that had 0 nodes. And so you come to the conclusion that in methane you have 4 bonding molecular orbitals, the one that has 0 nodes that is lowest in energy, and then the group of 3 that has 1 node that are all equal to each other in energy. The reason you know they're equal to each other in energy is from calculations and because they actually have the exact same shape, just oriented in different directions. All right. Yeah, go ahead.
How would the molecular bond of one node still be below the break-even point?
Why would the MOs with one node still be beneath the break-even point? That's a great question, and the answer has to do with the places where the wave function spans multiple atoms with the same sign. So the orbital we're looking at now, one of the 3 higher energy orbitals, takes up some of the space that would have been taken up by bonds in valence bond theory. So it's a bonding orbital. And another reason you know that, you focus on where the wave function spans multiple atoms with the same sign. Yeah, go ahead in the back first and then here.
We talk about liquid bond first. Where do we look for that? Do we look for the LUMO or the HOMO?
Okay, so the question is, if you're thinking about reactions and where they would happen first, do we look for the HOMO or the LUMO? We haven't actually introduced that term. It's from the study guide. We're going to talk about that in a minute. But in general, we're going to care about the high energy electrons because those are going to be the most reactive ones. So highest occupied molecular orbital. And then they're going to react with molecules that have a low energy empty spot for electrons to go, lowest unoccupied MO.
So where would you pick if you had, for example, just the molecular orbital period of the p orbital reacting with the hydrogens right there?
Yeah, so for methane, you would say and actually Spartan does this, the highest occupied molecular orbital is actually these 3 equal in energy orbitals with one node. And then it looks like the math tells you that I got the order of antibonding orbitals wrong, which isn't going to matter for us right now. But yeah, if you had to pick, you'd say, okay, HOMO is there, LUMO is there. Yeah. Was that your question in the front? Yeah? Okay. So let's see. Let's talk a bit about resonance and show you how we're going to need some MO theory to complement what resonance tells us. So I'm going to draw a molecule that happens to be called allyl anion. That's not its systematic name, it's just what we call it. I'm going to label carbons 1, 2, and 3. And this is a Lewis structure. I'm going to draw another Lewis structure with the same atoms all in the same place, but with a different arrangement of electrons. Instead of having a pi bond between carbons 1 and 2, I'm going to put it between 2 and 3. And instead of having a lone pair on carbon 3, I'm going to put it on carbon 1. I'm going to use this double-headed arrow to indicate that these are resonance structures. There are rules for generating resonance structures that if you're not sure about, you ought to review in the introductory study guide. I believe you've been exposed to resonance a little bit in general chemistry, and the rules are simple enough to learn. But in this class, you're gonna need to be able to know how to draw resonance structures of a molecule. And so if you're weak on that, you should review it. Resonance tells us that either of these molecules is an incomplete description of the allyl anion. It doesn't tell us that the double bond is switching back and forth rapidly between 1 and 2 and then 2 and 3, nor does it tell us that the lone pair is hopping back and forth between 3 and 1. Rather, it tells us that the structure of the molecule really should resemble something like this, where electrons are delocalized. And once you hear that word delocalized, you ought to think, okay, this is probably a situation where we're going to need some MO theory. I'm using a dotted line to indicate that the electrons in this pi bond are simultaneously shared across carbons 1, 2, and 3. And then I'm going to use a lowercase delta minus to indicate I've got partial negative charge on carbons 1 and 3, but not on carbon 2. And that's our resonance hybrid. I actually hate drawing resonance hybrids because where did all the electrons go? All of a sudden, I don't know how many electrons I'm doing. I prefer to draw out the individual resonance structures themselves. Okay. So let's see how we can apply MO theory to this situation. Let me ask you a couple of questions. What is the hybridization of carbon 3 in the resonance structure on the right? Go ahead.
SP2.
SP2, and you know that how?
Because it has one s orbital, two p orbital. Well, because I know that there's 3 of them. So
Good. 3 groups around that carbon must be trigonal planar, therefore sp2 hybridized, right? What would you say over here, though? You'd be tempted to say sp3. Go ahead.
SP2 because you can't change it up to SP3 since it's resonant, so the electrons will be localized all over.
That's right. You can't change hybridization in resonance structures. Resonance is about electron rearrangement, not about atoms moving. If you move atoms, it's not a resonance structure. Therefore, if carbon 3 is sp2 hybridized here, it must be sp2 hybridized in the resonance structure on the left. Now, if you had looked at that before you knew that and said, hey, there's 4 groups surrounding that carbon number 3, it ought to be tetrahedral and sp3 hybridized, that's a forgivable mistake. But now you know that in resonance you can't move the atoms, and so if it's sp3 over here, it must be sp2. I'm sorry, if it's sp2 over here, it must be sp2 in the resonance structure on the left. All right. Now, let's think about, from a valence bond perspective, what orbitals can contribute to the electrons that are involved in resonance. Where do we get the pi bond from? Go ahead.
Remember, like combining p orbitals?
Right. Yeah, we get the pi orbital by combining the p orbitals, one of them from carbon 1 and the other from carbon 2. Remember that on sp3, remember that on trigonal planar sp2 carbons, the sp3 orbitals that make the sigma bonds are all in the plane of the molecule, and the p orbital is coming out above and below the page. If we were to try to draw this molecule, and I'll try to show a plane on its side, the p orbital on carbon 1 and on carbon 2 come out above and below the plane of the molecule, respectively. Okay, what orbital contains the lone pair electrons? If that carbon is sp2 hybridized, and you've accounted for each of the sp2 orbitals in each of these sigma bonds, the only thing that's left is a 2p orbital, right? Lone, I'm realizing my trouble here, lone pair got to be held in the 2p3 orbital. Well, now if I draw it that way and line them all up, it starts to make me wonder, how do they know which ones are involved in the double bond and which ones are holding the lone pair? Maybe you don't. And in fact, what MO theory will tell us is we can take these 3 2p orbitals that we have, and they're on adjacent carbons, and they're lined up with each other. We can combine those atomic orbitals together to get 3 new delocalized molecular orbitals. Now hold on. In methane, we made molecular orbitals out of all of the atoms in the structure. Here we're only talking about a p orbital from each of 3 atoms. Why are we able to do that? The answer is that the sigma, all of the orbitals that are involved in the sigma bonds lie in the plane that I've drawn here. They're 90 degrees away from each of those 2p orbitals, which means they can't interact and they can't affect each other. So we're totally fine to ignore the in-plane framework of sigma bonds. We're going to call it the sigma framework. We can ignore that and focus only on the 2p orbitals. And if we do that, we're going to get the exact same answer that we would get if we did the full-on gut-busting, mix them all together at once that we did with methane. Okay? And that'll be general in OChem. We're often going to think about the p orbitals and pi type orbitals as different and not interacting with the sigma orbitals that they are orthogonal to. All right, so how do I mix 3 p orbitals together? We're going to do this by addition and subtraction like we did before for hydrogen, but we're going to do it one step at a time. So here are atoms 1, 2, and 3. And I'm going to start by adding a p orbital together on carbon 1 with a p orbital on carbon 2. I'm sorry, I'm getting ahead of myself. I'm going to add a p orbital from carbon 1 with a p orbital on carbon 3. And I'm just going to deal with that combination first. Sorry, I'm getting distracted with my colors. So this is the plus combination, 2p1 plus 2p3. And similarly, I could make the minus combination, 2p1 minus 2p3, only I'd have to switch the sign of the wave function, which I'm representing by color. All right, do you see how we got there? Just adding them together. Interestingly, anytime the sign of the wave function switches, you have a node. And actually in this 2p1 minus 2p3 orbital, we have a node that coincides with atom number 2, which is kind of interesting. Up here, or on the other side, there's no node, but there's also no space where there's electron density in between the 2 atoms. So what we'll do now is we're going to add in the 2p orbital from atom 2 by addition or subtraction. So, sorry, we'll just take this. I know the copy and paste is stressful to those of you that are trying to scramble and get things written down. Understand that the video will be posted and the notes will be posted as well. So don't worry about trying to get everything. I'm trying to resize this and it doesn't like me. That maybe gave you time to catch up. So if we add the 2p orbital from carbon 2 and we do it in phase, we're going to have this arrangement. Whereas if we add them together if we use the subtraction combination, subtracting the 2p2 orbital, what's left is this. Looks like that. Both of these orbitals have a node in the plane of the sigma framework, but some of them have other nodes. There's a node every place the phase switches. How many nodes does this orbital have? Okay, it's got one horizontal one and then 2 vertical ones. Okay, and what we mean by this is in between atoms 1 and 2, electron density goes to 0. In between 2 and 3, electron density goes to 0. From top to bottom, electron density goes to 0. And there are changes in wave function sign every place that the wave function goes to 0. In contrast, over here, we have only one node, the horizontal one. Yeah?
Why is it that the electrons are shared in the pi bond between all three, but for the lone pair, it's not shared by the two?
Good question. Why is it resonance tells you that the electrons in the pi bond are shared between 1, 2, and 3, but the lone pair is only on carbons 1 and 3, never on 2? To answer that question, really we're going to call this all in-phase combination pi 1. That is the lowest energy orbital because it has 0 of these vertical nodes. We'll call this one pi 3 because it has 2 vertical nodes. Now, we never dealt with adding and subtracting the p orbital from carbon 2 with this original subtracted orbital, right? But we don't have to, because it turns out it's not going to matter whether we add any orbital there. There's a node there. Electron density is 0 there. So actually, it doesn't make any difference when we mix in the 2p orbital on carbon 2, it still goes to 0 because there's a phase switch that coincides with that second atom. All right, so this orbital is pi 3, and the order, we would call that pi 2, and it has one node. The order of energy is pi 1, pi 2, and pi 3. How many electrons were involved in resonance in my original resonance structure? The 2 in the pi bond and the lone pair, so that's 4. So if we fill up the orbitals with the available electrons, we see that pi 1 is filled and pi 2 is filled. Pi 2 we would call our highest occupied molecular orbital because it's the highest occupied molecular orbital. Pi 3 we'll call the LUMO because it's the lowest empty one. Now, in the 60 seconds we got left, I want you to think about how the valence bond theory plus resonance corresponds with what the MO treatment of the pi orbitals gives you. Resonance told you that the pair of electrons in the pi bond between 1 and 2 was actually spread out also between 2 and 3. MO theory tells you that your lowest energy bonding electrons are actually spread out between carbons 1, 2, and 3. Exact same answer. And in fact, the MO picture tells you what those electrons actually look like. There'd be a lobe above the plane and below the plane opposite in phase. Second, resonance tells you that the lone pair electrons on carbon 3 are shared evenly with carbon 1, but they never are on carbon 2. And that's exactly what the MO theory result gives us. The highest energy electrons are in pi 2, which has a node on carbon 2, and that's why those electrons can only be on carbons 1 and 3. So we're going to see that for the most part, we can stick with valence bond theory as long as we remember the antibonding orbitals. But when it comes to resonance, we're going to have to be thinking about the possibility for these delocalized pi orbitals. Now, I went through the process of showing you where these orbitals come from. Thankfully for you, I'm not going to ask you to generate pi orbitals from scratch, but I will show you structures of pi orbitals, ask you to order them in energy, fill them up with the available electrons, and then choose HOMO versus LUMO. All right, and that just about does it for us today. So have a good evening, and I will see you Friday.